To have Professor Peter Scott presenting the 8 geometries of 3 manifolds.
Thank you. It's very nice to be here. See so many people. So what I'm talking about is mainly very old history by now. Most of the action took place in the 70s, but very recently, well, the last 10 years, Paragon actually proved the geometrization of projection. But I haven't got time to say anything about that, not that I really understand it anyway. So I'll talk right back at the beginning, where I'll start. So I guess the first thing to say is that until the mid-1970s, three-manifold theory existed, but there's no geometry in it at all. And so first to introduce the idea you should think about manifolds in this geometric way. And that's really what I'm talking about. So to try and give an idea what this is about, I'd actually like to start by talking about surfaces. So let's just start about the Euclidean plane, just for a minute. Everyone is very familiar with that, and of course Euclidean geometry, which I think everybody still does in high school. You drew straight lines and talked about distances between points and stuff like that. Well, the kind of geometry I'm thinking about is differential geometry. So you've all got calculus, you know what that's about. So if I draw a curve in the Euclidean plane, it has a perfectly good length, which you can find out by integration, what's long as a reasonable curve. And if you fix 2 points and look at all the curves between them, then the shortest one is going to be a straight line segment. So the straight lines and the geodesics in this particular Riemannian geometry. So this is the Riemannian geometry way of looking at things. And so now what I'd like to do is talk about compact surfaces and how these ideas for the geometries can be seen to be something very old, in fact. So if you look at the classification of closed surfaces, so there's a two-sphere and projected plane, which I'll put together. There's a torus and a Klein bubble, which I'll put together. And then there's the rest. So these are the higher genus of surfaces. So the top line is orientable genus of these two. So there's meant to be a representation of genus 4 surface. And here you get non-orientable surfaces. ORBLE stands for oriented. And there's a whole lot of them here. And that's the complete classification of closed surfaces, which I hope everyone is net. You can't quite prove it. Now, if you want to think about this geometrically, the place to start is a two-sphere. That's a very standard, nice object, which sits in Euclidean free space, unit sphere. And as we live on one, of course, a large one, we're very used to thinking about the differential geometry of this, even if you don't quite think of it that way. So on the sphere, if you take 2 points, when you measure distance between them, how do you do it? You do it in a differential geometry kind of way. So first of all, if we draw an arc on the sphere, it's of course an arc in free space, so I can evaluate its length by standard calculus. And the shortest arc joining 2 points is actually, of course, not a straight line in free space, but it's an arc of a great circle. If you've ever flown to Europe, you'll know you have to go much further north than where you start. So the geometry of the two-sphere is something you really understand. And so that's the geometry you see there. Now what about the projective plane? The projective plane is obtained from the two-sphere by taking the quotient. We just identify typical points. Now, I can't draw you a projective plane. Maybe somebody can. It's very hard to draw a projective plane. But we don't try and do that. The first thing to point out about the projective plane is that locally it's just a surface, just like the sphere. If I take a small disk center x and a small disk center x bar, so sorry, center minus x. Oh yeah, my vector notation, I put the line underneath. I believe in this country you put a line on top. There we go. It's part of my English education. So these two disks here get identified together, and the result is just a disk inside the projective plane. Now, the nice thing about that is, if I want to measure the length of an arc in the projective plane, let's draw it inside this disk, a short arc. If you can measure the lengths of short arcs, of course you can measure the lengths of long arcs by just integrating with the various bits. So I draw a short arc in a projective plane in this disk. Of course, what I'm going to do to measure its length is just lift it up into the two-sphere, take its pre-image. And when I take the pre-image of that short arc, I get two short arcs. And I'm going to find the length to be the length of either of these arcs, which is okay because they're the same length, because the net x goes to minus x on the two-sphere is an isometry. That's the key thing we want to point out. That's an isometry. So the projective plane, even though you can't draw a picture of it, has a perfectly good Riemannian metric in the sense you can evaluate lengths of any curve, and so it has GV6 and so on. So that's the natural geometry on the projective plane from the point of view. We're not talking projective geometry, we're talking differential geometry, just this quotient of the two-sphere. Now the two-sphere obviously has this property of being curved. If you stand at any point, that's called positive curvature. You can see it's this kind of shape. And the projective plane, even though you can't draw it, is like that too. At every point, somehow it's curved in exactly the same way as the two-sphere is. But locally, as I said, take a small piece of projective plane, it's exactly isometric to a small piece of the two-sphere. So you couldn't tell the difference if you lived on them. Maybe you live on a projective plane. Okay, so having said all that, that's the right way to think about those two things geometrically. Now the torus of the flying bottle, everybody knows what a torus looks like. It's like that. The surface of a donut. Well, that's not really a good way of thinking about the torus, actually. If you think about that surface sitting in free space, it's curved in various ways. It's got positive curvature like here, positive curvature and negative curvature here, where it's more like a saddle shape. So that is actually not the kind of torus I want to think about. I want to think of what's called a flat torus, and unfortunately you can't really draw one. So let's start, remind you that the torus is obtained from the Euclidean plane by taking the quotient by naturally C cross C. Or you can obtain it from, here's a picture of the Euclidean plane again, take a unit square, then I take translations, one horizontal and one vertical, for a unit distance, and I'll generate a tiling of this plane by translating that square. And if I take a quotient of the plane by this group action, it's the same thing as taking one square and gluing the left-hand edges together and the right-hand edges together. I'm sorry, the top and bottom edges together. But this picture is a much better way of thinking. This description is much better than that, because if you define a torus that way, it's kind of not obviously homogeneous. You have to think of it, you can say it's a surface, because of what's happening in the vertices. Think about it this way. Well, the projection of E2 to the torus is a covering map. And this, in fact, is exactly the same sort of situation as we had here. Here we have the two-sphere and a group of isometries acting on it. The group is just order 2, with the quotient of the projective plane. Here we have the Euclidean plane, and we've got a group of isometries acting on it, the C plus Cx by translations. And so T inherits a perfectly good flat metric. So if I draw a short curve on the torus, I lift it up into the Euclidean plane, I can lift it here, or here, or here. They're all going to have the same length, so it doesn't matter which one you take. I can work out the length of any curve on the torus, so it's got this Riemannian metric. And locally, that means if you stand on the torus, it looks just like the Euclidean plane. It's flat. So you couldn't tell the difference between the torus and the plane unless you go really a long way. So this is the kind of metric you want to think on the torus, but say this flat torus is not something you're going to meet in the real world. That's not a flat torus. Of course, the Klein bottle, everybody can draw. I hope there's a picture of one downstairs, an immersed Klein bottle in free space. But you can't draw an embedded one, so I can't even do that for you. But of course, this is also the torus factored out by some group. Or if you'd rather think about it that way, it's the torus factored out by some group of order 2 acting. But in any case, this group of Pyman of the Klein bottle acts on the Euclidean plane by isometries, or is E2 acting on torus by isometries. And so the Klein bottle also inherits a flat metric.